Okay, so today we're going to talk about section 4.1. I apologize in advance, my neighbor's using his leaf blower. I hate leaf blowers, just incidentally. I don't hate the people who use them, I just think leaf blowers are, annoying, especially when you're trying to make a calculus video. Anyway, so today we want to talk about section 4.1, and I'm going to spend more time talking about the distances aspect of this in class. But I want to start off with a very simple example. So this is going to be sort of a fundamental change in where the class direction is going. We've been talking about derivatives and some very concrete functions, and now I want to address the following question. So here's a portion of the graph. This is going to be y equals f of x, and the function is x squared. And I want to answer the question, so between the x coordinates 0 and 1 question, estimate the area under the graph of x squared from x equals 0 to x equals 1. So this is the question. So all of this area in here is what we want to estimate. So this is sort of the key word is estimate. We're going to try to determine this exactly in just a little bit, but here's how I want to do it. I want to do this by, see, this is a curve, and so we don't know how to measure, we don't have a formula for measuring the area of something like this sort of curvilinear shape. But we do know how to estimate or how to compute the areas of rectangles. And so we're going to try and do this just using rectangles. I'm going to just arbitrarily, just as a starting point, I'm just going to pick 4 rectangles here. So this is, the coordinates here are 1/4 and 1/2 and 3/4 and 1. Okay, and so I want to I want to use, so notice each of these segments that I've divided the interval from 0 to 1 into has length 1/4. So this is length 1/4, and this is length 1/4, and that's length 1/4, and that's length 1/4. Now I want to take at each of these points that I've marked from 1/4 to 1. I want to look at its corresponding point on the graph. Okay. And then up here, we're right here. And I'm going to use these 4 points to make rectangles. Okay, so here's what we're going to do. I'm going to draw one rectangle right here, and so the coordinates at this point are they're 1/4 and then 1/4 squared. Okay, and then the same thing here. I'm going to build another rectangle like this, and then maybe just, wow, it's really loud and annoying. I really hope that you can hear me over this. The coordinates at this point are 1/2 and 1/2 squared, right? Because the function is x squared. And then same thing here. I'm going to build a 3rd rectangle, and the coordinates right there are 3/4 and 3/4 squared. And then finally, one other rectangle, a 4th rectangle right here. And the coordinates here are 1 and 1 squared. Okay, so let's just let's sum up these areas right here. So I'll call it R4. This notation will be important. R stands for rectangles, and 4 stands for there's 4 of them. So R4 is going to be the sum of these 4 rectangular areas. Okay, and notice this is an overestimate. It's an overestimate because the rectangles all lie above the graph. The tops of these rectangles all lie above the graph. But let's see, so each rectangle, so the area of the first rectangle is 1/4 times 1/4 squared. Okay, and then that's the base, the length of the base, times how high it is. And we get the height from the function itself. We plug that coordinate 1/4 into the function, and we know how high it is. So that's the area of the first rectangle. And then the area of the second rectangle is 1/4 times 1/2 squared. Okay. Then the area of the third rectangle is 1/4 times 3/4 squared. And the area of the fourth rectangle is 1/4 times 1 squared. Okay. Now, just to be pedantic about this, I'm going to factor this 1/4 out here, and I'm just going to look at so we have 1/4 squared. Okay. And then I'm going to do something silly for later, but I'm going to do it now. So rather than write 1/2 here, I'm going to write 2/4. Okay. And then rather than write 3/4 here, oh no, I am going to write 3/4, of course. Yeah, 3/4. And then the last one, I'm going to do the most silly thing of all. I'm going to write 4/4 squared. Okay. So this is the area of the sums of these rectangles. All right. And if you add these up, you get, I'm cheating, I'm looking aside, 0.46875. Okay. So this is an estimate using 4 rectangles. Let me just make sure this is all showing up on camera. Okay, it's all showing up on camera. My camera's on a tripod, so sometimes it gets knocked, and I want to make sure that I don't lecture for 20 minutes here off camera. All right, so this is an estimate using 4 rectangles, and they're rectangles that have their right endpoint on the graph. Okay, so this is right rectangles, 4 of them. Okay. Now, the reason why I point this out is because we could make this much more precise here. We could try something a little bit more extreme. We could try using 8 rectangles. So I have 1 and 1. And I'm just going to draw this again. Okay, same function, x squared. And now instead, same question. So same question with 8 right rectangles. Okay. So, all right, I have to, okay, that divides it into 2, that divides it into 4, and that divides it into 8. Okay, and let's do, remember this silly thing that I did before. I wrote 1/4, 1/2, 3/4, and 1 as 1/4, 2/4, 3/4, and 4/4. I'm going to do that here as well. So this is 1/8, this is 2/8, this is 3/8, this is 4/8, this is 5/8, and so on. Okay, so we've got 1/8 through 8/8. Okay, and now we're going to do exactly the same thing. I'm going to build 8 rectangles here. So notice what I'm doing. I'm starting down here. I'm drawing up there till I hit the graph, and then I'm completing the rectangle like that. Okay, so starting here, drawing up till I hit the graph, and then headed over to the left and completing the rectangle like this. I'm just going to keep going like that, like so. This takes just a tiny bit of practice to do, but not too much practice. Again, notice this sum of these rectangular areas is going to be an overestimate because all of the rectangles have some area to them that's not contained below the graph of this. But if you look very closely at this picture, okay, so here's the picture with 4 rectangles. It looks to me like there's more overestimated area here than there is here. There's a little less area that we overshot by on this one. So we're going to call this R8. And again, it's going to look like this. It's going to be 1/8. That's the width of the rectangle, times, and then we get 1/8 squared. So this is area of rectangle 1, okay, plus, and then we have 1/8 times 2/8 squared, okay, This is area of rectangle 2. Okay, and then so on. And we'll let's see, we'll get to 1/8 times 7/8 squared. That's the area of this 7th rectangle. And then one more, 1/8 times 8/8 squared. That's the last rectangle. Okay. So now, if we look at all of this, we sum this up. I'm going to factor out the 1/8 again, and I get 1/8 squared plus 2/8 squared plus dot 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 plus 7/8 squared plus 8/8 squared. Okay, and you'll remember what. So I want to recall for you our notation for summation, which we talked about the other day in class. So here's our notation. I'm counting something up from 1 to 8 here. So I'm going to do that. I'm going to do n equals 1, and I'm going to go to n equals 8. And then I have 1/8 right here. And then inside of here, I'm going to count n, and I'm going to count, so n over 8. So starting at 1, we make n 1, and we get 1/8 times 1/8 squared. So that's the first piece. And then we get 2/8 squared, so we have a 2 in here, and so on. So this is our summation notation for this. And if we compute this, well, let's see. If we compute this, well, I don't have access to this number, but a closer estimate than with 4 rectangles. Okay, so this is the this is estimating with 8 rectangles this time. Okay, so now let's do this just more generally. So here's our picture. I'm going to try to do it a little bit smaller here. 1, 1. We have the graph of x squared again. And we're trying to find this area. Okay. So here's our general procedure for this. Divide. This is our procedure. 1. So we divide the interval from 0 to 1 into n subintervals. So all of length 1 over n. Okay. So here's how you do that. So here's 0. We're thinking of this as 0 over n. Here's 1. We're thinking of this as n over n. And then we have 1 over n right here. And then we'll have 2 over n right here. And then we'll have 3 over n. And then we're going to just keep wandering up until we get to, well, let's see, we'll have a couple. Here will be n minus 1 over n. And right here will be n minus 2 over n. So this is so n is the number of chops you want to make here. And this is our way of counting. Okay. So notice, how did we get this? We got this by taking the right endpoint and subtracting away the left endpoint and dividing by n. Okay. So this is our first step. This is going to give us a sequence of endpoints to use for our. This is going to give us a sequence of endpoints to use for our rectangles. Okay. So these are going to be our rectangles like this. Okay. So these are going to be our rectangles. Now, step 2 is we compute and sum the areas of the right rectangles. Compute and sum the areas of the right rectangles. for these subdivision points. Okay, so here's what we mean by that. So we have, in this case, remember we're using the right endpoint of each of these. So Rn, this is right rectangles, n of them. We have 1 over n times 1 over n squared plus 1 over n times 2 over n squared. So this is area of the first rectangle right here, and this is area of the second rectangle right here, and this is area, and then we have area of the third rectangle, which is 1 over n, 3 over n squared, and then we keep going up to 1 over n, n minus 1 over n squared, like this, and then the last one, 1 over n, n over n squared. Yes. So this is rectangle 1 area, rectangle 2 area, rectangle 3 area, and on till we get to the last rectangular area here. So this right here, you can put any number in for n that you like. And I want to go back to our observation. The more n's you use, the more rectangles you use, I should say, not the more n's. The higher the n means the more rectangles. The more rectangles, the better the estimate. So the more rectangles, the better the estimate. Okay. So I need more space here, so let's so in summation notation, this previous formula for Rn looks like this. This time we're counting up to n, so I need a different counter down here. We're going to start at 1 right here, and we had 1 over n. Remember, n is fixed here. N is fixed. It's the number of rectangles that you want to use. Okay, so we have 1 over n times, and then we have I over n squared. Okay, so that's what this piece right here. How we interpret this sum in summation notation. Every term of this sum is being multiplied by 1 over n here, and our counter is going 1 over n, 2 over n, 3 over n, on and on. So we indicate that with this notation. So we want to do just a little bit of juggling here. So we get so we'll have I squared times 1 over n cubed, right? There's 2 copies of n in the denominator here, and 1 copy there, so we get n cubed right there. And then we have I squared, and I is going from 1 to n. Okay. So now, if we just look at this for a minute, since n is a fixed number, it comes right out of this. And what we're actually doing here is we're doing 1 squared plus 2 squared plus 3 squared plus up to, so we have n minus 1 squared and then n squared. Okay, so all I did was I factored that 1 over n cubed out of this expression, and now I'm left with the sum of the first n squares. Okay, so now there's a formula for this that obviously I don't want you to memorize. Formula use for this. So the formula for this is, well, the 1 over n cubed just comes along, but there's a formula for this part, the sum of these things. So this is equal to n times n plus 1 times 2n plus 1, and all of this is over 6. Okay. Now, so I want to, we have to do a little bit of juggling of this formula here. Let's expand this out. We'll have n times n plus 1, so that's n squared plus n. And then we have 2n plus 1. And down here we have 6n cubed, okay? I'm not done expanding it. I am going to expand this a little bit more. So we get 2n cubed, okay? And then we get 1 copy of n squared here and 2 copies of n squared here, so that's 3n squared. And then we're going to get 1 copy of n. Okay, so this is our formula for Rn. So this is key. So this is, no matter what n is, this is the area of n right rectangles. Okay. For x squared from x equals 0 to x equals 1. Okay. But now, remember our observation from before. The more rectangles you use, the more accurate this estimate becomes. All right? And so that's analogous to taking a limit. So the area, the true area under f of x equals x squared from x equals 0 to x equals 1 is what you get when you take the limit. It's the limit as n goes to infinity of Rn. Since this is super duper important, I have to check one more time that this is showing up. It is. Okay, beautiful. So we want to take the limit of this, but this is just a limit of a ratio of polynomials. So we really are only looking for the highest power of n. So here the highest power is n cubed. Here the highest power is n cubed. So the limit of this as n goes to infinity, if we remember our limits, our infinite limits, our limits at infinity from a few sections back, is just the ratio of these two leading terms. So that's 2 over 6. So that's a third. Okay. So if we take the limit, of Rn as n goes to infinity is the limit as n goes to infinity of 2n cubed plus 3n squared plus n over 6n cubed. This is just 2 over 6, which is a third. Okay, so that tells us that there's exactly exactly 1/3 a unit's worth of area under here. So that's kind of cool. We computed this precisely. So let me give you the general formula for doing this. So in general, so if we've got a function between a and b, and you want to know this area, okay, and this is our function, the graph of y equals f of x. Then step 1, you take b minus a, divide by n. This is the length of this. So and we call this delta x. So this is the width of the rectangle. Width of the rectangles. Now remember, we're going to take, so right here, this is going to be a plus 1 over n. The next one will be a plus 2 over n, and so on until we get to b. Right. So we divide the interval from a to b into n pieces, and then excuse me, and then we set up a system of points here. So we're going to call this one, let's call it x1. We'll call this one x2. So xi is going to be a plus I times b minus a over n. I shouldn't write that. These aren't 2's and things. Well, we'll leave this as is. So a plus I times b over a minus n. So how does that work out? So we get so this is a plus I times delta x. So if we're thinking about the interval from a to b, then when I is 1, this is a plus delta x. When I is 2, this is a plus 2 times delta x. When I is 3, this is a plus 3 times delta x. And we just keep adding increments of these delta x until we get to a plus, and then will be n minus 1 delta x here. And then b is going to be a plus n times delta x, which, if you think about it, delta x, remember, was b minus a over n. So when you multiply that by n, this is a plus b minus a, which is b, okay? So it all sort of works out. We start at a, we just keep adding lengths of delta x until we get to n copies of them, and then we're at b, okay? So we have this, so these are called our sample points. These xi are the sample points, okay? And then step 3, we form a sum. So I'll do step 3 here. So these are, again, these are for right endpoints here. In step 3, we form a sum. So we're summing i's starting at 1 and i's going to n, and we're taking our delta x. Okay, this is the width of a rectangle right here. So rectangle width, and then we're going to take f and evaluate it at the sample point. So this is the rectangle height. And so this is all, these are all for the ith rectangle. The product of these is the ith rectangular area. And so we're summing all of this stuff up. So so let's rewrite this. So I is starting at 1, and I'm going to write in, so f of a plus I times b minus a over n. This is this piece right here, written this is rectangle height, and then we're multiplying by b minus a over n. Okay, this is rectangle width. Okay, all I did was took this fancy X language and put it in terms of A's and B's and this sort of thing. Good, very good. So this is the rectangular area of n rectangles. The area under f of x from A to B is, so area is equal to the limit as n goes to infinity of this expression. Okay. This I will expect you to know by the exam time. We'll talk about this, we'll supplement this with some lecture in class and go from there. But for now, we'll use this to carry through. Now, here's what, here's the point that I'd like to make just before this video closes out here. I'm going to make as much of it as I can before I run out of time here, or battery power. So suppose for a minute that this is a velocity graph. So instead we're in the t situation. So suppose that this is v of t, it's a velocity. Okay, right here. Then, and this is time. Here. So now if we did any number of rectangles through here, right-ended rectangles here, just drawing in a few rectangles, then this rectangular area, one of these rectangles has one dimension is time and one dimension is distance over time, because that's velocity. Okay, So if you do time times distance over time, then the units of area here are just distance. Okay, so that's absolutely key. So that means that that area under a velocity graph is distance traveled from time A to time B. To time B. Okay, we'll think more about this in class.